Hello, here we go with some more forces questions. We've got a block of concrete resting on the ground as shown in this figure. So it's given us the dimensions. Is there anything that they haven't told us in the picture? Yes, so we've got a density there of the concrete. So calculate the weight of the concrete. Right, so we need to do the volume multiplied by the density multiplied by G. So we've got 15 multiplied by 0.8 multiplied by 1.2 multiplied by 2.4 times 10 to the 3 multiplied by 9.81. So it's quite a lot of things to put in. 2.4 times 15 times 0.8 times 1.2 times 9.81 is 339, so we make that 340, and then I've got the 10 to the 3 as well, so 3.4 times 10 to the 5 newtons weight. Pressure exerted, so calculate the pressure exerted on the ground by the block of concrete. So that's force over area. We've got the force. The area, well, I assume it's standing on the oh yeah, saying 1.2 high. It looks like that anyway. So we've got the 0.8 times 15. So we have to divide by 0.8 times 15. So divided by 15 is that. Divided by 0.8 is that. So we've got 2.8 times 10 to the 4. 2.8 times 10 to the 4 pascals. So it's a nice pair of starters. Figure 7.2 shows two vertical walls supporting a uniform horizontal platform in equilibrium. Net force acting on the platform is zero. State another condition. Right, this is just to remind you or make you think that you know about moments. So we need to have the net moment is also equal to zero. So we can say about any point really. So yeah, any axis, but the net moment about any axis point is equal to zero. That's fine. The walls exert upward forces on the platform, and engineers suggest that the wall X should be moved a little further away from the centre of gravity. Yeah, because it's a bit wonky, so it wants to move it that way of the platform, and the opposite wall left where it is. Yep. State and explain the effect of this change on the force exerted by wall X on the platform. Right, okay, well, it's clearly going to decrease. I mean, you can see, and we know this just from everyday experience. I mean, if you've got something which is nearer the centre of it, is taking most of the load. So we know it's going to decrease, but we want to have a better, more scientific explanation of why. So we could say that the moment about the other wall, about the left wall, is the same, is unchanged because it's still in equilibrium. So the moment about left wall is unchanged. We've got the distance is up, so force must be down if we're going to keep the moment the same. So yeah, nice little question. That's quite a simple one, really. All right, next up, we've got Apollo 11 was the first manned spacecraft to land on the moon. Figure 1.1 shows part of the equipment left on the surface by the astronauts and the forces acting upon it. Right, so they've left, I don't know, left their TV behind. According to Newton's third law, interacting forces always occur in pairs. The student states that the normal contact force N is equal in magnitude to the weight W because of Newton's third law. Okay, give two reasons why the student's statement is incorrect. Right, okay. Well, first of all, Newton's third law, you have to have the same force acting on different bodies. So it's got to be the same type of force, and they've got to be acting on separate bodies. You might remember this from when we were discussing it in an earlier video. You've got quite a formulaic way you can write the sentences. So you can say, force, for example, force due to whatever exerted by A on B is equal to force due to, again, the same thing. This must be the same thing, so we'll call that X maybe, exerted by B on A. So we need to have two things in this. We have to have two separate objects and we have to have the same type of force. So I'd imagine these are the two reasons that they're asking for here. So we can say that he's wrong because we don't have two objects. Both forces are acting on the equipment that is drawn here, I think, isn't it? Yes, so we got the weight of the equipment and the reaction force on the equipment. So both forces act on equipment. But Newton's third law requires two objects, and then we can say the forces are of different types. We've got one gravitational, one contact or electrostatic, different types, but Newton's third requires same type. Requires, if I can write it properly, one type. So yeah, that's fine. Yeah, people tend to get a bit mixed up with Newton's third law. I find this approach of knowing that you've just got this really formulaic way of writing it out, that these have got to be the same. It's got to be the same force here, and we're just flipping the objects round. Force of A on B is force of B on A, and the same type of force. That kind of brings everything into clarity then, I think, when it comes to Newton's third law. Use Newton's third law to state the magnitude and location of the force pairing up with the weight W. Right, okay, so we can use now this approach at the top. So we can say that the what are we doing here? We're saying that the force due to gravity, magnitude and location, force due to gravity of Moon on A, on equipment, i.e. W, is equal to the force due to gravity of equipment on Moon. So it's equal to W acting on the center of mass, i.e. W acting on center of gravity, acting on center of gravity of Moon. But again, you can see that's all coming from this way of writing out Newton's law here, Newton's third law, this sort of syntactical approach that we've got. Right, part B. While on the surface of the Moon, one of the astronauts hit a golf ball with a club and declared that it went for miles and miles. I think that was a later visit to the Moon, but I could be wrong. The ball was given an initial velocity u at a fixed angle theta to the horizontal. Show that the horizontal distance travelled by the ball is directly proportional to u squared. Right, so this is all, I mean, whether we're on the Moon or not doesn't really matter on all of this. This is just a straight projectiles question, really, isn't it? So we're going to say that the time of travel, we can get that first of all. So we're going to have, if we use s equals ut plus a half at squared, just change the colour on this. So if we're using that, so we've got no change, that because we've come back to where we started, we've gone up and come back down in the vertical direction. So vertical direction, we've got u, which is going to be u sine theta multiplied by t, which we're going to cancel in a minute, minus a half of at squared. So that's all of that. So we can then cancel the t's because we know that we've got one solution at t equals 0. One solution t equals 0. We want the other solution. So we're saying here that t is equal to 2u sine theta divided by a. we now multiply this. So in this direction, we can then say that the distance travelled, I think that was what I wanted, the horizontal distance is just going to be equal to u times t. So that is u cos theta multiplied by t, which is 2u squared sine theta cos theta divided by a. So we've got exactly what they want. So s is proportional to u squared. So that's just a standard playing around with projectiles question, really. It doesn't have anything to do with the moon. I think maybe they're just trying to confuse matters of, well, what are you going to use throughout it? Is there anything strange you're going to do? You're going to get mixed up with accelerations for some reason. But it's just a straight projectile sort of derivation. All right, next up we've got figure 2.1 showing an object held horizontally by a string. Right, this has got moments written all over it looking at this picture. See what's in the text isn't in the picture. One end of the object rests on a support, other end held by a string. The object is in equilibrium. Point G is the center of gravity. The mass of the object is 1.2 kilograms. 1.2 kilograms. The tension in the string is 5.1 newtons. Okay, string makes an angle of 40, well, that's meant to be degrees, well, look at it with the vertical. Yep, they've marked that on. Take moments about the support and calculate the distance d. Right, so g multiplied by d, not g, 1.2, g is the point of the location of center of gravity, 1.2 g multiplied by d, so that's little g multiplied by little d, is equal to, what have we got, 5.1 cos 40 multiplied by 3/4. All right, mixing my decimals and my fractions, which isn't really great. So d is going to be equal to 5.1 over 1.2 g times 3/4 times cos of 40 degrees. So we just have to whack that in. Well, we got 5.1 divided by 1.2 divided by 9.81 multiplied by 0.75 multiplied by cos of 40 degrees equals 0.249, so 0.25 meters. Explain why the force at the support cannot be vertically upwards. Right, well, if it's in equilibrium, there's no net force on it, so, and there's a component of the tension, in horizontal direction. Yeah, we could say there is a component of the oh, I missed out even the word tension. There's a component of the tension in the horizontal direction, so there must be a component of the force at the support to counteract this if the object is to be in equilibrium. So something along those lines. There has to be no net force on the object if it's in equilibrium. There is a component of the tension in the horizontal direction. So there must be a horizontal component to the force at the support in order to counteract this. Whatever way you want to word it, it's all the same sort of thing. Figure 3.1 shows the stress against strain graph for a metal X up to its breaking point. Right, so stress against strain, fair enough. Used figure 3.1 to state the physical properties of this material. So properties, so we're wanting at least two of them here. So one of them is brittle because it's just snapping at the end here. So brittle is going to be number one. The other thing is going back where it started, is elastic, because it's got this, you stretch it out and it goes back again. So brittle and elastic is fine. It's returning. There's no plastic deformation, I think is maybe the other way you could put it, as in we're not ending up back at some point, a strain which isn't back down here at zero. So yeah, so brittle and elastic are the only two things I can think of at the moment. So that must be, at least that is properties. we've got more than one. On the axes, sketch a graph for a ductile material have a larger Young's modulus value than the metal X up to its breaking point. Oh, right, okay, so note the commas, right? So we've got to sketch the graph up to its breaking point, and have a higher Young's modulus. So the Young's modulus is the gradient, so we need a steeper gradient. So we need to have some straight line. So that's dealt with the first bit of the larger Young's modulus. But then we need to have something which is ductile, so it will have some kind of plastic deformation or something going on. So we want to have some weird sort of, they do these sort of things going on, where you get this massive increase in the extension without any increase in the stress, or even a decrease in the stress. So yeah, so that's all good. Figure 3.2 shows a stationary cable car. Good. Well, maybe not that good if you're sitting on it. Wonder why it's not moving. The cable on both sides of the car is at an angle of 12 degrees. They're doing these weird letters again. To the horizontal. The radius of the cable is that. The stress in the cable is that. Okay. The Young's modulus of the material is that. Okay. Calculate the strain experienced by the cable. So Young's modulus is stress over strain, and we want to get strain. So strain is equal to stress divided by Young's modulus. What have they given us here? So the stress is 1.8 times 10 to the 7. Yeah, and what was the Young's modulus? 2 times 10 to the 11. So we've got a 0.9 and a 10 to the minus 4. So 9 times 10 to the minus 5. Should probably put a 9.0 on that, considering what they've given us. So 9.0 times 10 to the minus 5, and that has no unit strain. That's the extension over length one. So we're okay with that. But I put 9.0 because we've got a 2.0 and a 1.8. So let's keep to two significant figures. Calculate the tension T in the cable. Right. The radius of the cable is that. Right, okay. So we've worked out, so we've got stress is the force over the area, and we've got the area. So which one are we? Stress number, oh, it's the 1.8 times 10 to the minus 10 to the 7. Force over area, so for 1.8 times 10 to the 7, that's our stress. We need to multiply that by the area. So that is going to be pi r squared, pi times 2.6 times, squared times 10 to the minus 4. We can square that one straight out. So get rid of that, make that a 3. Right, we've got 2.6 squared multiplied by 1.8 multiplied by pi is 38.2. So that is, let's say, 3.8 then times 10 to the 4 newtons. So yeah, that's just knowing what stress is. It's easy to get mixed up with some of the numbers here, but that's come out okay. Calculate the weight of the cable car. So weight is going to be equal to, if it's just stationary, 2 lots of 3.8 times 10 to the 4 multiplied by sine of 12 degrees. So 7.6 multiplied by sine of 12 degrees is equal to 1.58. So we say 1.6. So 1.6 times 10 to the 4 newtons. Right, there's a nice mix of stuff in that. Yeah, we've had Young's modulus, we've had graphs, we've had working out the strain, and then we've done a nice forces equilibrium thing at the end. So yeah, there's lots of little bits in that. to round off this mini video. I'll do more forces in the next one.